we see a summary of these ideas. Pendulum of length L at displacement x, tension is approximately equal to mg, the weight. The x component is the weight times x over L. Now we're representing the weight by mg, and this all works for small x over L. All these approximations work when x over L is small, and they work very well, in fact. So that for small displacement, we get a net force of negative Tx. Now I've just dealt with the magnitude of Tx, haven't really worried about the direction, and maybe should have. But when x is positive, if we pull the pendulum back this way, the force is in this direction, negative. The force is obviously in the opposite direction to the direction in which we pull the pendulum back. So it's in the opposite direction to the displacement, is what I was trying to say there. The acceleration is therefore negative Tx over m. Now, what's Tx? That's negative mgx over L. Divide by m, you get acceleration equals negative g times x over L. And in a minute we'll see that we can take this acceleration and use a little bit of calculus, and I'm going to show you the calculus. If you're in a calculus-based course, then of course you need to know the calculus. If not, you should appreciate it because you can understand most of what I'm going to talk about here. So if we come over here and look at a sequence of equations here, a sequence of reasoning actually, we see that in the first place, acceleration is the rate at which velocity changes in time. We would think of delta v over delta t, but in calculus we take this to the limit. We say that the instantaneous acceleration is dv over dt. And then velocity, of course, is delta x over delta t, if x is the direction in which the thing is moving, which as a limit goes to what we call dx over dt, the derivative of the velocity function, and the derivative of the acceleration, or derivative of the position is a velocity function, derivative of velocity is acceleration function. Just one simple step from the delta v over delta t and so forth. Then we're going to say that the acceleration, which is dv over dt, where v is dx over dt, is going to be the second derivative of x with respect to t. And if you don't know the calculus, you kind of understand this. If you substituted a dx over dt up here, you would kind of have some squares, but these things don't act exactly like algebraic quantities, and you might wonder why the d down here isn't squared and so forth, and just accept that for the moment. Now, since acceleration is negative g times x over L, as we just found from the analyzing the forces, then we conclude that this expression for the acceleration is equal to this, and we get this equation. Second derivative of x with respect to t is negative g over L times x. Now, what's a solution to this equation? Well, x is a function of t. Okay, and the solution to the equation is a function x of t that solves this equation. Just to make a plausibility argument, depending where you are in calculus, you might understand this more or less well. We're taking a second derivative of some function, and we're getting a negative multiple of that function. Same function. What can we take a second derivative of and get a multiple of the function? Well, second derivative of an exponential function of an e to the kx is going to be some constant times e to the kx. But when you take two derivatives, the constant's going to end up being squared, and it won't be negative. There are also sine and cosine functions. The second derivative of the sine function, remember the derivative of the sine is the cosine, and the derivative of the cosine is negative the sine. So the second derivative of the sine function is negative sine function. So maybe x could be some kind of a sine function. If you took the second derivative of the sine of the quantity kx using the chain rule, and you maybe ought to pause and do that before you go on if you're doing the calculus-based course. Second derivative of sine of kx with respect to x. Okay, what you get is negative k squared times the sine of kx. So that if k was equal to the square root of negative g over L, you would actually have a solution to this equation. Now, for calculus students, that's going to be straightforward, and besides, your text is going to tell you exactly the same thing. This equation has solution x of t equals a, any constant, because the constant is going to be invisible to the second derivative, times the cosine, using the cosine instead of the sine. I could have used either, but the cosine works better for visualizing the pendulum, as you'll see. But a times the cosine of the square root of g over L times t. Okay, and that's going to be our function. So that the solution to this equation, one solution, is this function. Another solution would be with a sine here, and that gets into phase angles and so forth, and we can talk about that, but that's going to go a little beyond the scope of what I want to talk about here, where I'm trying to concentrate on the basics. So, this is where the cosine dependence comes from. Now we're going to relate that back to what we observed on the reference circle.